Electron configuration is a method of assigning electrons to where we think they might be in the atom. We think they might be in orbitals, which are probability regions that have specific amounts of energy. They're quantized. And the orbitals are in sublevels. And in the previous video, we looked at the order of increasing energy of the sublevels. So the lowest energy orbital is 1s. So if you have just one electron, then you would put it in the 1s sublevel. Now, an s sublevel can actually hold a maximum of 2 electrons. So we could put 2 electrons in the 1s sublevel. But once we've done that, it would be full and we'd need to move on to the next one, which is 2s. S can hold 2, so we could put 2 in that one. And then when it's full, we could move on to the 2p sublevel, and a p sublevel can hold 6 electrons. Okay, so then when 6 electrons were in 2p, it would be full, and we'd have to move on to 3s, etc. So that is how we write electron configuration. We assign electrons to orbitals in these sublevels, and when the sublevels are full, we move on to the next one. So let's do an example. Let's do sodium. Sodium has 11 electrons. So we'll start in our lowest energy sublevel, which is 1s, and it can hold 2 electrons. So we write that as 1s2. Now that sublevel's full, we move on to the next one, 2s, and it can hold 2. So we've assigned 4 of the 11 electrons. So we just keep on going till we've assigned all 11. So after 2s, we have 2p. P's can hold 6. So far we've assigned 10, 2, 4, 10. So now we have 1 left over. Let's see what comes after 2p. After 2p comes 3s. So we're going to write 3s1. Now you should always sum your superscripts, 2, 4, 10, 11, to make sure we've assigned all of the electrons in an atom. Okay, the way I've written that configuration is called a full electron configuration. Now, another way of writing it is to write an orbital diagram. So orbital diagrams represent orbitals as boxes. So the 1s sublevel contains 1 orbital, so we draw it as 1 box. It can hold 2 electrons, and we represent the electrons as arrowheads pointing up and down. It's actually half an arrowhead pointing up and half pointing down. And that actually represents the fact that the electrons are spinning in opposite directions. And we have 2s, 2. When we draw the 2p sublevel, the p sublevels contain 3 orbitals. So we draw the p sublevels as a rectangle split into 3 boxes, and we fill them one at a time, 1 electron at a time in each, and then we go back and pair them up. And that's because Hund's rule says that orbitals with the same amount of energy will fill with just 1 electron at a time before they pair up. Okay, and those 3 orbitals have the same energy. So we put 1 electron in each, and then we go back and we fill them. And then we have 3s, contains 1 orbital, so it's 1 box. It has 1 electron, so it just gets half an arrowhead like that. Okay, so this is the full electron configuration. Let me write that, full. This is the orbital diagram. And then we have one other method of writing electron configuration, and that is the noble gas core. Now, noble gases, as we know, let's take a look at the periodic table. Noble gases are in group 8A. And we learned that they contain 8 valence electrons, and that's very stable. It's very stable because its valence shell, or its outermost shell, is full. So if I was to write the electron configuration of neon, which has 10 electrons, I'm going to write the orbital diagram because I think it's a nice visual tool. We've got 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6. Notice that its valence shell, n equals 2, is completely full. Okay, we've got no unpaired electrons. We've got a filled valence shell that's very stable. And if you look at the difference between neon and sodium, you'll see the only difference between those 2 electron configurations is this electron right here, 3s1. Okay, so as we know, chemists are lazy. We don't like to write things out longhand. So a shorthand method of writing electron configuration is to choose the noble gas from the period above your element. Okay, so let's take a look. Here's sodium, it's in period 3. So the noble gas in the period above sodium is neon in period 2. And just represent neon's electron configuration, or whatever noble gas you pick, by just writing the noble gas in square brackets and then writing what comes after it. So instead of writing 1s2, 2s2, 2p6, 3s1, we can just write neon 3s1, because neon's configuration is 1s2, 2s2, 2p6. So it's just a shorthand. Instead of having to write all of this out, we can just write neon in square brackets. And we call that the noble gas core notation. Sometimes the noble gas core configuration. And it's just a shorthand method. Okay, so there's 3 different ways of writing electron configuration: full, orbital diagram, or noble gas core notation.